Hello, this is Jonathan Gardner, and today we're covering section 2.5 motion diagrams of Surway and Jewett's Physics for Scientists and Engineers, 9th edition. You can get a copy, thankfully, to its, get a free copy, thankfully, to its generous copyright. And today we're covering not as much as we did in the last video, where we talked about the second derivative and acceleration. By the way, if you're watching these videos on YouTube, you probably want to use the playlist to watch these. You probably don't want to just have them pop up in your feed. And I plan on putting these together on a website so that you can click through on the website and watch the videos one after the other. 2.5 motion diagrams. So this section exists to try to help you understand what's going on more from a hand wavy part with acceleration and velocity. And I think this section exists because of the confusion that people have about this topic, which would be okay if it wasn't a very important topic, but it's a critical topic. Like, I don't really understand how you can study anything in physics without really catching what's going on here. Calculus and physics are tightly integrated together. And if you don't understand calculus, or if you don't understand the concepts, and you get some false conclusions because of your bad understanding, you're not going to get anywhere. In fact, you're probably going to go opposite and end up hating physics and hating math and hating the world. And so let's just let's look at this thing in another way. So it's called a motion diagram, and what it means is we're going to basically, you know what a strobe light is. So a strobe light, it just blinks like every second or half second or whatever, right? And otherwise it's pitch black, you can't see anything. And if you're in a room with a strobe light and no other light source, then you just get these snapshots of what's happening, right? And so we're looking at particles and how particles move, but you can imagine a car or a toy car or something like that on a track or something like that maybe. And so we're going to look at first what constant velocity looks like when you do a strobe light. So we're in the room, okay, and the first strobe light goes off, and there's where the car is at. I'm not going to draw a picture of a car, but there's where the car is at. And then it goes off a half second later, and there's where the car is at. And another half second later, and there's where the car is at. Another half second later, and there's where the car is at. And so on. So as each strobe goes off, the car is moving an equal distance because it has constant velocity. The change in the position, which is velocity over time, is not changing, so it's constant. So it's boom, 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 boom. Okay? Now suppose you're in a room and you had a toy car on a track or something like that, and instead of the pictures being the same distance apart, it starts off they're close together, and then as time goes on, they get further and further apart. Okay? And what you're left to conclude here is that the car is moving faster and faster, right? At first it's moving slowly, it's just boom, boom, boom. And then down here it's like boom, boom, boom. It's moving very quickly, right? And a third case, maybe it's the opposite of that case up there, where at first it's going rapidly, but then it slows down. And then it almost stops, right? And so this is kind of the opposite. Okay, so this is constant velocity, and we can measure the average velocity for each of these snapshots just by drawing an arrow from one picture to the next. And what do you notice about this arrow is it's always the same direction, and it's always the same size. So we're basically taking this arrow and we're moving it, and the arrow isn't changing, just the location of the arrow is changing. But remember, vector quantities, we don't care where the vector is. We just care which direction it's pointing and how big it is, how magnitude. And in this case, all of these vectors, the average velocity vectors, they're all the same. So we have constant velocity here. But in this case, we do the same thing. We just draw an arrow, tail to head, tail to head. And what do you notice about the arrow? Is it the same arrow? No, the arrow is increasing in size. So it's getting longer. And so we say, well, the arrow's getting longer, so let's see what's each point, what is the change in the length of that arrow. It's just a little bit each time. Okay, So between this arrow and that arrow, it's just a little bit of a change. This same thing here, same thing there. They're always the same thing, right? So the change in the velocity arrows is the acceleration. So this is the acceleration. This is the velocity, right? And then for this one, you notice the arrow is getting shorter each time, right? And so how much shorter is it getting? Well, it's getting shorter by that much. Same amount each time. Okay? And so the acceleration and velocity here, the acceleration is opposite the velocity, right? Notice we don't use the word deceleration. We say acceleration is pointing left or it's negative. Acceleration is pointing right or it's positive, right? That's the kind of terminology we use. So this hopefully helps you understand kind of what's going on. Oh, by the way, you could have, so this arrow is the position, then the second position, and then the third position, and so on. It's kind of useless to draw that because we're on the page. We can see that, right? So quick quiz. Which one of the following statements is true? A, if a car is traveling eastward, its acceleration must also be eastward. So if a car is going down the road in an eastward direction, the acceleration must also be eastward. Think carefully, is that true or is that false? And if it's false, why is it false? Okay. Statement B. If a car is slowing down, its acceleration must be negative. So for this statement, you just have to think of a case where a car is actually speeding up with negative acceleration. So what would that look like? Okay, remember, slowing down, speeding up is referring to the speed of the car, which is the magnitude of the velocity. It doesn't tell you which direction the velocity is going, it just tells you how big the arrow is, right? And statement C, true or false? A particle with constant acceleration can never stop and stay stopped, right? So a particle with constant acceleration can never stop and stay stopped, right? So it could stop, but it won't stay stopped. Right? That's what it's saying. Which one of those statements is true? Are they all true? Are they all false? If they're false, what's false about them? Is there something you can do to the statement to make it true? That's a quiz for you to do in your own time. Guys, have a great day. Take care. Bye-bye.